So we should be on YouTube now,
Okay.
with a slight lag. So people will tell me if something went wrong. All right, so hopefully we're both audible and well, fitable. All right, so this is the latest as of the current moment in the worldwide Neuro Talk series.
Mhm.
And first of all, we need to say thank you to Tim Foggers of the University of Oxford, without whom none of this would have happened. So thank you, Tim Foggers. Next, I should probably say a couple of things about who we're looking at. So I will start with myself because I'm privileged that way. Uh, so I'm Philip Bartle of the laboratory of Thomas Baden at the very sunny Sussex over in Britain. And I have Dr. Peter Neri,
Doctors.
uh, but who is so he graduated in Pisa, Italy, um, in the Scuola Normale. I think you will pardon my pronunciation.
Yeah. No, no, don't.
And then followed that up with a PhD in Oxford, um, followed up by a bunch of postdocs in places like Stanford and Berkeley. Um, so pretty much the talk will speak for itself. I'll just say, as a way of introduction, perhaps that it truly Peter's papers have never ceased to amaze me with their ingenuity. So, and his talks just never fail to be very enlightening and entertaining. So I think that we will have that today. So without Peter Neri, so
Thank you,
please.
Tom. I mean, thank you, Philip and Tom. I want to thank both of you. So, but thank you, Philip, for the introduction. And shall I go on share screen now, or?
It's talk. You can do whatever you want.
Okay, so at this point, I have full control. And if at some point the connection doesn't work, please let me know, and I'll yeah. Yeah, sorry. Okay,
I
so
will.
just share the screen.
Mm-hmm.
I'll do it right now. Okay. So if it's working fine, then you're just gonna leave me up there, and then if there is a problem, yeah, you. Okay, perfect. So thank you to all of you who are following. Obviously I can't see you, so it's a little bit weird. But if you have questions, please do ask the questions. Philip told me that he has a way of getting them over to me. And I'll be happy to stop and explain. Also, because I realize that a lot of you in the audience may not be familiar with psychophysics and psychophysical techniques. So the topic of the talk today that I'm going to give is about scene processing and natural scene. So that's the main topic of the talk. And I'm going to start out with just a kind of a cartoon view of how we think primary visual cortex operates today. And again, it's just a cartoon, and I hope the video will not crash the live stream. So this is kind of a cartoon of how we imagine that visual cortex is sampling the image using these localized detectors that are attempting to extract some property of the environment of the visual stimulus, such as, for example, orientation or spatial frequency and so on. And we know we have reasonable models of how this happens, although there is still a lot to be figured out. And we also know that if you add stuff around the localized region that is analyzed by these detectors, such as this kind of rich contrast defined pattern, then the response properties of those localized detectors change. And again, this change here in this video is affected by these green arrows. This is again just a cartoon representation. And we have, again, reasonable models of how this happens. But this is not what I want to tell you about today. So the topic I want to explore today is what happens when this stuff that appears around the localized detector turns into objects that we can interpret, understand, recognize, and so on. And the influence of this additional stage of processing is represented here by these magenta arrows that are impinging upon the receptive field. And in this particular cartoon, what they do is they cause a change in the sharpness of that wavelet. But this is, again, just, just a cartoon representation. So this is a summary of what I just showed you. We have these stages whereby we imagine that the properties of this local visual detector are impacted by the presence of stuff around it, and in particular, stuff that makes sense, like natural scenes. And so what I'm going to tell you about today is, first, I'm going to start with some not too technical aspects of how you can psychophysically characterize an object of this kind. So within a reasonably simple context. And then I'll move on to what happens to that characterization as you switch, for example, to a natural scene, such as you can see here. But the focus will be primarily on modeling in terms of, so I will not give you a lot of detail on the modeling, but the psychophysical paradigms are geared towards a paradigm that can be approached via modeling. And so, for example, we will try and build a model of the local process and then attempt to describe how it may be impacted by the interpretation of the scene. And then there is this additional stage that you saw that in between, going from just a blank image on the left here to the full natural scene, which I will describe provisionally as the object segmentation stage. So basically the talk is structured around these three different stages and the way they interact on different levels. We're not going to assume that, for example, it can only go feed forward. It can also go via feedback, the interaction across these stages. And as I said, the focus will be on attempting to obtain characterization that can be modeled using models of this kind that you see here. So relatively simple models. And let me see, before I move on, I just want to just spend 1 minute addressing the question of why should you go about this, this problem in this manner, which is not the only manner of approaching natural scene perception by any stretch of imagination. There are many different ways that you can approach scene perception. For example, you can ask a human observer to determine whether there's an animal in the scene or there is a house and so on. Why would you want to do it locally, as I'm going to show you throughout this talk, and why using these tools? And the primary reason is that I'm interested in modeling. So I want to be able to model the process, and it's very difficult to do that using psychophysical data unless you adopt this kind of paradigm. So that's the primary reason. So let me move on to just give you a little bit of background on the physiology, and which I imagine many of you can relate to perhaps more easily. I just don't know your background. But this is an example of a very early paper looking at how the receptive field of a visual neuron may be impacted by the presence of natural statistics. So as you can see, this started pretty much at in the 21st century. Physiologists became more interested in this problem. And as you can see, there were some attempts to measure changes such as this one as you transfer to a natural context. And then from then on, over the coming years, there were more and more articles in physiology looking at neuronal properties in response to natural statistics, all the way to current research. So we like to imagine that these neurons, the way they respond, has some impact onto how we perceive scenes, obviously. And so the question really is, how do these changes in the neuronal properties would then transfer onto a behavioral response, such as this one, where you ask the human observer to determine whether they saw an object or not, which is a typical standard psychophysical paradigm. And surprisingly, there is very little that we know about this question. So I was actually discussing this with Philip earlier. So the emphasis in the field that is put on neuronal recordings and electrophysiology, and I sympathize with that and a lot, and having actually first-hand experience of recording from neurons. At the same time, it's I find it often interesting how there doesn't seem to be much concern in the field for how we then we understand the link between these the neurosubstrate and the behavioral response. And of course, we can make a lot of progress understanding neurons, but unless we understand this link, we have not really figured out very much about how the brain works. So we really need to understand this connection. Of course, it's a very limited connection in a psychophysical context. You're still asking people to press buttons and so on. So that's a different problem, but at least you're closer to the perceptual aspects and the behavioral aspects of this problem. So I'm going to start with what I title here simple things first. In fact, it's not simple at all. It's just that what I mean to say is that I'm going to illustrate the techniques that I use, that I'm going to use in the talk with simple visual stimuli, simple laboratory artificial stimuli first, and then move on to natural scenes. So imagine that you have, for example, a human observer who's asked to detect the presence of a wavelet such as this one, which is, as you all know, is very common, wavelet of this kind in visual neuroscience. What you can do is you can superimpose a mask, a noise mask, onto the stimulus. And then we imagine that there is in the back of the brain of the observer, there must be some mechanism, some transducer that translates this visual stimulus onto a button press. Yes, I saw the stimulus or I didn't. And so there is this perceptual coupling here. And what you can do is you can apply a technique that's actually now quite widely used in visual psychophysics, which is to reverse correlate the noise inputs with the behavioral response from the observer. Essentially, what you do is you look at how specific samples of the input noise impact the response from the human observer. And by reverse correlating that, so by using the response to analyze the noise in a response-dependent manner, you can obtain a picture of the sort of perceptual filter that the observer is applying to the stimulus in order to generate the binary response. And I don't have, I can't really give you detail, more than this much detail about this technique, because otherwise it would take too long and then I wouldn't get to the main topic of this talk. If you have questions, of course, ask them. I hope you're able to ask them now, otherwise at the end of the talk, I'll try and clarify. And for the moment, I think you can just think of this intuitively as a technique to map the sort of receptive field of perception, although it's by no stretch of imagination as simple as that. And there are many complications with this way of thinking about it too. I think one simple way of understanding how the technique works is to imagine that what happens if the observer is ignoring the monitor. So imagine that your observer is simply doing something else and pressing buttons randomly. What will happen in that case is that if you apply the same analysis, you will just get noise back. The reason being that the perceptual coupling at that point is essentially eliminated, and therefore there is no correlation between the specific button press and the specific noise samples that you present. So you don't get a perceptual filter back. And so, as I said, we can image the perceptual filter using this technique. And we can also do it not just in 2D, as you've seen here. So what we're obtaining here is a spatial map of the receptive field. We can also do it across other dimensions. A dimension that I will be talking about throughout the talk is the dimension of orientation. And an efficient way of mapping this is to first build a basis of oriented wavelets spanning the whole orientation axis, as you see here. Then you can apply a random contrast to each one of those wavelets on every trial. So this is essentially orientation noise. And then you sum them all up and you superimpose them onto the stimulus, onto the target. This is essentially just a way of injecting orientation noise. It looks sort of like that. When you apply the same technique, what you obtain here is an orientation tuning function now. So this is the perceptual filter, but instead of being defined across 2D, which is, in this case, the noise was defined across 2D. So of course you get the same dimensionality for the filter. Here it's going to be defined across orientation. And as you can see here, the shape of this filter looks sensible, just like the other one here that looked very much like the targets. Here you get a positive peak at the vertical target orientation, that the orientation you had asked observers to detect. You also get some other features that are not as obvious. For example, you get these negative troughs at the orthogonal orientation that are not necessarily to be obtained under all protocols. And then you can use this information, this data, that is, if you collect enough trials, it's going to give you quite a detailed picture of the perceptual process, to develop models. So here, for example, is a particular model that I've put in here. It's a very popular model in visual neuroscience. It's a gain control model. As you can see here, the shaded area that explains both the orientation tuning function well and the 2D perceptual filter. And I've spent many, many years trying to figure out how to get this right, how to choose the right noise, how to do the right experiments, and eliminating all sorts of artifacts and so on, developing good models for it. And so after, I would say maybe I got a little bit bored after 20 years of doing this. And so I decided to see if I could take this toolbox and transfer it to natural scenes. And so that's really the question I'm going to address during the first part of the talk. So how do you take these tools that are essentially tools that have been developed and validated within low-level vision and transfer them to questions having to do with higher level vision and natural scenes? And I'm going to show you data that is mainly published already, so these articles here, but also some unpublished results, in particular with a postdoc of mine, Lorenzo Landolfi, who I'm working on at the moment on this project. So there will also be some relatively new material. So how do we transfer all this toolbox? The way I decided to approach this was to essentially carve myself a region within the natural scene where I could define everything, the statistics of the noise and everything, without interference from the natural scene. So I effectively remove that part of the natural scene and then graft a low-level target, such as a wavelet, or in other cases, a bar, into the natural scene. But the way this insertion is done is not by just superimposing the wavelets at any orientation onto any part of the natural scene. It is done in a way that is relatable to the structure of the natural scene. So for example, as you can see here, the wavelet has been inserted into the scene so that it is aligned with the structure defined locally by the natural scene. So this is essentially a hybrid stimulus where you have a low-level stimulus that is embedded within a higher level stimulus. So that's the first trick, is to use a combination of these two. And then once you've done that, well, you can just apply the same paradigm that I described earlier. So now what you can ask observers to make a choice between the wavelets being correctly aligned with the structure of the natural scene, so congruent, I will refer to it here, or incongruent, meaning that it is orthogonal to the structure of the natural scene, as you can see here. And then what you can do is you can apply noise to the stimulus, orientation noise, for example, just like the one I showed you earlier, but I'll give you also examples later of the 2D spatial noise. And you can apply exactly the same technique, because as I'm sure you can recognize, the paradigm is not that dissimilar from the one I showed you earlier. But there is a fundamental difference, which I will describe in a second. So what you can see here is that when you apply that kind of technique, you will get, this is real data, both curves show real data. This is the one you showed earlier, you saw earlier for a simple vertical target detection task. And here is for a congruent, incongruent task. And as you can see, superficially, the two traces don't look that different. There are some differences, but overall, they seem to be to share the same characteristics. But there is a fundamental difference between these two descriptors. So this one here is defined in absolute coordinates, by which I mean it is defined in the coordinates of the monitor. So when I say vertical here, if you take, for example, this point on the x-axis here, vertical refers to vertical on the monitor. This was actually a vertical stimulus. When you take this 0 point on the x-axis for this descriptor here, it refers to the orientation that was congruent with the local structure of the scene, whatever that orientation is. So really, this is a scene coordinate. It's a coordinate that is referred to the structure, to the meaning of the scene. So for example, that congruent orientation could have been any orientation, could have been vertical, could have been diagonal, horizontal, or so on, depending on what the scene specified locally. And this is an important difference because essentially what we're doing is we're applying a coordinate transformation to all of the toolbox that I described earlier, the reverse correlation technique, the stimulus, the local stimulus, the modeling, and so on. We're just transferring to this new coordinate system where we can start asking questions that make sense in the context of the structure of the scene. And so I'm going to give you a few examples. So now we're switching to the scene, and let's consider this particular natural scene. This is just one I'm going to use as an example throughout the talk, but of course in the experiments we use many different scenes. This is a good example of the kind of problems that you encounter in this data set. So consider these two regions here. You can see that in this region, there is a well-defined edge. It's well-defined by contrast energy, whereas here, there is virtually no edge being defined by contrast. So in this slide, what you see here in blue is the energy content, the edge energy content across the image. So the more intense the blue, the more edge energy there is. So as I described earlier, this region has much more content, much more edge energy than this one here. And the tuning function that I showed you earlier, the orientation tuning function, refers to this kind of scenario where there's a poorly defined local region, local edge, where we place the probe to obtain this characterization. So now we could ask what happens to the orientation tuning function when we go from a region like this to a region where the physical image contains much more information in terms of just sheer contrast and physical content about the local edge structure. And when you do that, perhaps surprisingly, you find that there is very little change in the tuning characteristics of the perceptual process. So I'm going to refer to this as poor and this as rich on this particular map, which is essentially a physical image map. So now consider these other two locations and let's compare these two. So if you look at these two locations in terms of edge contrast energy content, they are very much the same. In fact, here there is barely, it's almost just a uniform gray background, just as this one here. So there doesn't seem to be much of a physical change when you go from here to here. There is no edge here. But in fact, there is a boundary here. The boundary, of course, is your perceptual representation of the scene. And it is the boundary between the table, which is the main object in the scene, and its background. So it's an important figure ground cue. And so here, what I'm doing in green, I'm plotting the significance of that boundary for your perceptual representation. So for example, as I told you earlier, here, this boundary it exists in your percept, so it's well marked, and this one isn't. And just as an aside, for those of you who are interested, the way this map was constructed was simply by essentially measuring how many out of a sample of observers will report this edge as being salient, as being important for representing the scene. So here, for example, virtually all of participants did. and very few participants marked this edge as being relevant to the representation of the scene. And this is actually BSD 500. It's not a dataset that I developed. It was developed at Berkeley. I just took it. It's available. It's freely available. So now we can ask a different question. We can ask what happens to the perceptual tuning function as we go from a region that is poorly represented in the percept to one that is richly represented in the percept. And as you can see here, in this case, there is a change in tuning. In fact, what we find is that the orientation tuning function is more sharply tuned around the orientation congruent with the scene for the locations in the image that are richly represented in the percept. And just from considering the shapes of these functions, you may wonder what do they translate into in terms of performance. So remember that observers were asked to do a local discrimination, so we can measure sensitivity, we can measure how efficiently they can detect, they can perform that discrimination in noise. And that's what I'm going to plot here. So it's a D prime, but in fact, it's the difference in D prime between rich and poor on the perceptual map here on the y-axis, and rich and poor on the image, the physical image map, so the image-driven effect here. And just from looking at these curves, you may expect that D prime should be better for the rich location on the percept as opposed to the poor one. And there shouldn't be much of a difference here for the physical image content. And in fact, that's exactly what you measure. There is a twofold effect on D prime, which is quite a substantial effect. Each data point here is one observer. So normally when I will show you scatter plots, each dot will represent a different observer. So now let me just give you a few reasons why I think this result is surprising. The first reason is that if you take just the local region in the image where the probe was inserted, that you can see here, and you put it over here, so this is just a small icon showing that local region. And this is the region around the probe. It's not just the probe, but it also includes the region around the probe. And you keep on populating it. So you do for all the different natural scenes that were used in the experiments. What you will find is that as you go from locations that were poor in the physical image to those that were rich in the physical image, there is an obvious change in contrast, in edge contrast, as you go from poor to rich, from left to right. And this is trivial, because this is exactly how they were defined in the first place. So those edges were defined, those local regions within the image was defined as such. They were defined as being either physically poor or rich. So this is not surprising. What is perhaps surprising is that when you compare the top with the bottom, this comparison is based on rich versus poor on the perceptual saliency map. And as you can see, just looking at the local region around the probe, there is, statistically speaking, on average, there isn't any difference. You cannot really tell which one would be rich and which one would be poor on the perceptual map. And yet, D prime goes exactly in the opposite direction. So what I'm saying here is that if you were just to imagine that the human sensitivity for performing the task goes with what you judge just by visually inspecting the local region around the probe, you would expect the D prime should be better for rich versus poor on the image-driven axis and not on the other axis. Instead, what you observe is the opposite, which is rather surprising. The other finding that is perhaps maybe surprising to some of you is that there is no effect of spatial attention. Let me explain this in relation to the paradigm. So one thing I didn't mention is that when images show up with a probe, they also are either preceded or followed by a white blob that you see here sometimes. So for example, this is a case where the blob followed the natural scene. That's a case where it preceded it. So that's a cue that tells you where the probe is going to appear. And it's either a pre-cue when it appears before or a post-cue. So it's an obvious manipulation of spatial attention. And what you find is that performance does depend on this manipulation, overall performance. So the cueing manipulation is working and observers are better at performing the task when the cue appears before the probe so that they can deploy attention to the probe. On the other hand, when you measure this differential effect on D prime due to whether the location in the image was perceptually salient or not, or whether it was physically represented in the image, there's no effect of cueing. So there is an overall effect of boosting performance by attentional deployment, but there is no, it's not modulated by the saliency of the image. And one last result, which I will come back to towards the end of the talk, is the fact that if you invert the scene and you produce this impossible scene, there is no effect, meaning you still measure this perceptually driven effect on D prime. So it doesn't really matter for the phenomenon that we're looking at here, whether the scene was upright or upside down, which I will try and interpret later on, but it's just to anticipate, it's related to the fact that the phenomena we're looking at with these experiments are connected with object segmentation rather than object interpretation. So how, I mean, if one were to interpret all of these results, given current thinking about vision, the story would go as follows, essentially, that initially you have your circuitry that is devoted to analyzing the localized region within the image that is rich, is physically rich. So you that is the part that is monopolized, that monopolizes the circuitry. And then later on, as your brain constructs a representation of the natural scene, it renders regions that were physically represented within the image that are de-emphasized, and those that are emphasized are those that were perhaps poorer in the physical image, but are now perceptually well represented over here. So then, of course, there is a feedback process that would go back and change the properties of the localized sensor. And that's how this feedback story goes. But what I'm going to show you is data and considerations that actually make this interpretation unlikely. So the first problem with this feedback story is that it's very hand-wavy. So I've tried to represent that here. And one way perhaps that we can make it a little bit more concrete is using modeling. And that I will quickly demonstrate. I won't give you much detail here, but it is possible, for example, to capture this retuning of the perceptual orientation tuning function using a simple gain control model, such as the one that I mentioned at the beginning, and by changing some property within the model that I won't get into the detail of. The point is you can account in detail for this psychophysical data using simple models. Then, of course, you're left with the problem of who is feeding the signal to make the local circuitry switch from one mode to the other. So who is interpreting the image? And here, of course, it's a much larger problem, and it's not at all a problem that is solved. So one thing I forgot to mention that I should mention at the beginning is that this talk, I will obviously will not be able to give you complete answers to the questions that I posed at the beginning. Is mostly just a way of demonstrating some tools that can be used to achieve those answers. So one possibility here is to use deep convolutional networks. So in this case, I used a network that by the standard of machine learning now is ancient. It's Dinosaur 2015. At the time, it was a recent model. And this particular this implementation of deep nets can do object segmentation. So for example, you feed it a natural scene and it will give you contours for objects within the natural scene. So what you can do is you can now relabel the human data, but instead of using the labels on the images that I described earlier as being the perceptually salient parts, you relabel them as the ones that are returned by the network as being important for representing objects and so on. And when you do that, what you can see is that you do get an effect in the data that is driven by this model labeling that is in the right direction. It's not as big as the one that was observed with the labeling I used earlier, but it's in the right direction. And this is not a trivial result. Just to show you an example, if you use another model from computer vision that at the time was actually quite successful before the deep network revolution, this model doesn't show any shift consistent with the data at all. So I'm just now moving on to another problem with the feedback theory. So not only it's poorly defined, this notion of feedback, at least within the context of perception, so that yes, we can model different parts of it perhaps, but we don't have a full model of it. The other issue is that feedback takes time. And if you base an estimation of how long it should take on what we know from the physiology, it would probably be at least more than 100 milliseconds. And there is a problem with this. I have a lot of data that argues against this this notion in the context of these experiments. The one I want to show you is data from EEG. And the reason I chose to do EEG measurements for this particular question of timing is actually an interesting one that I will bring up at the end of the talk again, because I'm also interested in hearing your opinion on this, which I view as an important methodological limitation of psychophysics, which is that I'm not convinced that there is a good way psychophysically to measure time to completion for a perceptual process. So I decided to use EEG to answer this question. So what I'm going to do now here, up here, I'm going to plot an EEG marker of rich-poor comparison. I don't have time to go into the details of how it's computed. We can, if you're interested, I can tell you at the end. By the way, this is published. So I'm just referring to it as an EEG marker of this rich versus poor comparison. And I'm going to plot it over time for different electrodes. In particular, the layout will be like this. You'll have the occipital electrode, central and frontal here over the span of time. So this is what that plot will look like when the EEG marker is pegged against rich-poor as defined in the image via that green map that I showed you earlier. So you can see there is some modulation. In particular, this is the interesting modulation I'll focus on later. This is the equivalence map for that EEG marker, again, electrodes versus time, for the physical image labeling that I described earlier, the blue map, so to speak. So I won't go into the details of the statistics here and so on, it's all published, but I will just say that there is virtually nothing of any significance here, except for this region within this perceptually driven map. So I'm going to focus now on this region and the equivalent region down here. I'm plotting you here the marginals across time of that activity within these two regions. You can see there is quite a bit here within the first 100 milliseconds in this map for the occipital electrodes, but none over here. And then what you can do is you can take that measurement for each observer and plot it over here in the same format in which I plot the psychophysical data earlier. So you will remember the psychophysical data for behavior, for sensitivity, was showing an effect along the y-axis that was perceptually driven. And this is also what you see for this particular part of the map for this EEG marker. And this is just a replication using either natural scenes or cutouts of natural scenes, which also work. So it's two independent replications of this result. And just to remind you, this activity here is very early, so it's within the first 100 milliseconds, and it's presumably sensory, if we believe the EEG can make that kind of spatial discrimination, occipital and parietal. There was nothing, as I had originally expected to find when I designed these experiments within the central and frontal electro region. So this is obviously hand waving, but just a potential link with the physiology is a link with what is emerging from recordings in V2. I've just chosen this study. There are many others that are showing similar data, whereby this boundary ownership signal that you may have heard of, whereby neurons prefer, for example, one side of the figure ground configuration as opposed to the other one, they show this preference very early within the first 100 milliseconds. So it's possible that these experiments behaviorally are targeting a stage that is equivalent to boundary ownership and subsequent object segmentation. Let me see how I'm doing for time. Yeah, should be okay. So now I want to move on to the third stage that I showed you in the tripartite image that I showed you at the beginning with the three different stages. So as I mentioned, there was a middle stage that was object segmentation, and the data I showed you so far, I think relates primarily to that stage. Then there is this other stage, which I'm vaguely going to refer to as the semantic stage. And it's the stage where we make sense of the scene, where we interpret it. But of course, if we want to study it, the problem is that this boundary is not very well defined. It's a faint boundary between segmenting and semantics. So we need some sort of operational definition of this transition so that we can measure it experimentally. And one interesting manipulation that is often used in psychophysics and actually in other areas of vision neuroscience that are interested in this question of natural scene is upside down inversion. So the idea here is that if you flip an image upside down, you still retain object segmentation because, yes, the table now is up here, but you can still segment it as being an object. On the other hand, when you move on to the next stage, which is the semantic interpretation stage, if the table is up in the air, then your interpretation of this object as being a table will be somehow impaired and disrupted. And I'm sure you're familiar with the large literature on phase processing and inversion. There's also a lot of literature on biological motion and so on. In general, the notion that you can disrupt semantic interpretation of visual stimuli using an upside down inversion. Of course, the nice characteristic of this manipulation is that all other aspects of the image are left unaffected. So spatial frequency, content, contrast, and so on. That's the idea. So here, to demonstrate the effect of inversion, for these experiments that are actually unpublished, so this is the unpublished set, the task was similar to the one I described earlier, except the target here was a line that, as you can see, was, again, either aligned with the natural scene or orthogonal to it. I'm not showing it here. Then noise was this sort of 2D spatial noise superimposed onto the line. And here on the right, you can see an example from data. This is more than 100,000 trials of human data, where you can see a characterization of the wavelets that the perceptual filter that observers are applying in order to detect that line. And as you can see, it looks very much like a line. So now what we can do is we can compare this object, this perceptual filter, as we measure it, when humans are looking at the upright natural scene as opposed to the inverted natural scene. And the main result that you observe here is the following. So if you look at this wavelet, it has content of both the orientation that is aligned with the scene and the one that is orthogonal to the scene. So there is energy at both orientations. So it's kind of a mixed wavelet that contains energy at the two orientations. And then in the upright case, there is much more definition for the orientation that is aligned with the scene and much less for the orthogonal orientation. So this is represented here by this cartoon where there is less intensity of the orthogonal orientation. So it's as though in the inverted case, you start with a sort of isotropic filter, and then it becomes more tuned along the structure defined by the natural scene, which I'm sure you can recognize bears some relationship to the effect I showed you earlier for orientation retuning around the orientation congruent with the natural scene. This is data from individual observers, so each dot is one observer. And just to, this is a little bit of a dense plot, but I'll walk you through it. Here on both the X and on the Y axis, you go from a value that if it's low here on the two axes, it refers to a wavelet that is a mixture of the two orientations. And then as you move along the axis here, it becomes more sharply tuned for the orientation congruent with the scene. I won't go into the details of how these measurements were taken, but essentially the main result is that if dots fall here on the lower parts of the graph, they indicate that the wavelet is more sharply oriented. It contains more energy at the orientation congruent with the scene than in the inverted case, which is it is the case and it is significant. Now, one difference with these experiments compared to the ones I showed you earlier is that in this case, we also had spatial cueing, but we did observe quite a substantial effect of spatial tuning on the structure of the perceptual filter. So for example, here between the pre-cue trials and the post-cue trials, so remember here on pre-cue trials, spatial attention can be deployed to the local wavelets. On post-cue trials, it cannot be deployed. You see a difference that is similar to the one I showed you for upright and inverted. So in the post-cue trials, when there is no attention, you tend to get a representation of both orientations And whereas in the pre-Q trials, you get a sharper alignment with the structure of the scene. So these two effects, and this is represented here for individual observers, you can see the data points clearly fall below the unity line. In fact, the effect of attention in this case is stronger than the one of inversion on this realignment of the perceptual filter. So it appears that these two mechanisms are tapping onto perhaps the same circuitry in order to reshape the perceptual filter. And here is just the results of some simulation using modeling with a gain control model. Here is the intensity of gain control, and that is modulated as an attempt to capture the human data. Again, I can tell you more about the details of how this difference with the human data was computed. Essentially, we're measuring how well the model can account for the human data as a function of this gain control part, the intensity of gain control for the inverted data. As you can see, there is little gain control in this case, and for the upright data, in which case there is more gain control, presumably because this gain control term is reshaping the perceptual filter to represent only the main drive, which is aligned with the natural scene. And the interest of doing this kind of modeling, I apologize that I don't have time to go into more details. And anyway, this modeling is still ongoing. So our efforts are moving in different directions in attempting to capture the data set, which is much larger than what I've just shown you actually. The interest is that if we were able to find convincing evidence that human vision can be modeled using this kind of localized models in the context of natural scene processing, then the link is, there is an existing link with literature that has appeared now a few years ago, but it's ongoing, by Cohen Cagley and Odelia Schwartz from our lab, where they've developed models based on neuronal recordings of how the surround in a natural scene impacts the properties of the receptive fields of neurons. And what they generally find is that this can be well modeled using a modulation of gain control. So the gain control term can be modulated by this surround in ways that depend on where you are in the natural scene. So the direction in which we're thinking is that maybe we can find a common ground with those modeling efforts in physiology. Of course, this leaves open the question still of who is doing the interpretation of the whole scene. And this is not a question that at this stage, for example, that line of research in physiology is addressing. And it could be, I don't know, deep nets that can be used. And then there are these more vague terms like semantics and top-down. And to finish off, this is the last piece of data I want to show you, is another example of perceptual filter retuning, this time in relation to phase rather than orientation. So here, observers, very similar to the experiments I showed you earlier, they were asked to to discriminate the orientation of an edge that was either aligned again with the natural scene or orthogonal to it. This is the kind of receptive field, perceptual filter that you measure for an inverse correlation for a human. As you can see, it's sensible. It has the shape of the wavelet that more or less of the edge that observers were asked to detect. And then again, you can ask the same question: what happens when you perform these measurements separately for inverted scene and for upright scene? And here, what you find, this is all published, so that I won't go into the details of the statistics to demonstrate the effect, or but it is an effect that exists. But as you can see, this wavelet contains more of a mixture of odd and even phases. So for those of you who are not familiar with this, even phase is this kind of wavelet that is essentially a line. So you have a positive region into that. The odd phase is just an edge. So other terms that you can use is edge and line. So this perception filter has roughly an equal content of line energy and edge energy, whereas this one here in the upright case has more energy at the edge configuration, which is this odd phase as opposed to the even phase. Again, as if when you go from inverted to upright, the perceptual filter was sort of polarized towards aligning with the structure of the natural scene. And this is shown slightly better here by taking marginals across the surface plot. And as you can see here, there is roughly an equal content of even and odd modulation, whereas here there is more odd modulation than even modulation. If you're interested in the individual observer analysis and so on, you can refer to this data, to this paper here. So what I'm going to try and do now with the few minutes I've left is summarize what I've told you with this sort of cartoonish approach. I know it's kind of embarrassing that it's still so hand wavy, but it's a big problem. So that's the best I can do essentially at this stage. Maybe 10 years, who knows, I can give you a more detailed picture of this problem. So the idea, the way we're currently thinking about this is that the data we're looking at is reflecting this kind of increasing refinement of the perceptual filter as you present a natural scene. So you start out with your circuitry, your visual circuitry, your perceptual circuitry that is essentially in an unbiased isotropic state. So all the different orientations are represented, all the different phases are represented, for example, a line-like phase, an edge-like phase, and so on. This is at the beginning of performing visual processing on a scene. Then as you develop an object segmentation, as your circuitry is performing object segmentation, it then works as an oriented attractor. So it essentially polarizes your previously unbiased circuitry towards taking on a configuration that is more consistent with the local structure of the natural scene. So you can see that now the wavelets are oriented along the segmented image. And we think that we can capture this using relatively simple models. And then there may be other stages. The one I showed you is a stage which I will refer to as phase alignment, where subsequently even the phase of these wavelets can be polarized to align with the structure of the natural scene by this additional semantic stage where we actually attribute perhaps identity to different objects such as the table and so on. And from the data that we have at the moment, this last stage depends on attention, whereas this one seems to be impervious to attention. And as I said earlier, therefore, this stage, I'm not sure I would characterize as top-down, and that I will leave for the discussion. Before just finishing up, so I think I'm doing reasonably okay time-wise. I apologize to you guys that I kept you so long. I just want to show you just a clip from some experiments that we're performing at the moment. I have some data, but I don't have time to tell you about it with virtual reality. So obviously now with headsets are so cheap that we can easily try and do these experiments in virtual reality. So in this example here, you are inside a room in the HMD, and what you will be doing is a task very similar to the one I showed you earlier for just people sitting in front of a monitor. So here you have these objects in the scene that look like boxes, essentially, with well-defined edges. And as you can see, sometimes you can see that probe appearing, that one over there, that's again, a wavelet within it. And observers have to perform a similar task to before. They have to decide if it's congruent or incongruent, and so on. And you can apply the same tools that I showed you earlier and determine whether there is an effect, for example, of doing room exploration and so on. So I'm just going to finish off by putting up these 3 questions that I would like to hear your opinion about, and which I mentioned throughout the talk. And then, of course, I will be very happy to take your question and answer them if I can. A few questions that come to mind for me that are important is how do we define top-down from the point of view of a psychophysicist, which I think is very different than the definition that a physiologist would give. And what can we do about modeling the module that interprets the image? And then there are also some methodological questions that are unresolved in my mind, as for example, whether psychophysics can be used to measure how long it takes for a perceptual process to complete. And that's all I wanted to tell you. So thank you for your attention. Philip?
Am I audible?
Yes, now you are. I can hear you.
Oh gosh, I don't know whether I'm audible or not. Sorry, this will be a bit silly because I cannot hear you on Zoom right now. I will.
Maybe.
Could Maxime maybe say something? I think you're already in the conference. Yeah, I'm sorry, Peter. It's just that literally for some reason I cannot hear you on Zoom, so I hear you with a lag of several seconds. Maxime?
I mean, I can hear you well.
Well, I know that you can hear me. I cannot hear you. So I will.
Hello, Peter. Can you hear me? Peter? Hello, Peter.
Yes, I can. But Zoom seems to be, it's strange because I can't, for example, I cannot exit my share here. Stop share.
Okay, this is a bit weird. Peter, can you hear me now?
Yeah, I can hear you.
Okay, perfect. So we have a bit of a problem apparently with Philip. Thanks for your talk. We have actually one question from Tom Padden, who's asking, in natural scenes, for example, without man-made objects, probably the horizon is a consistent, meaningful feature. Is there any additional level of representation for such more natural boundaries?
So wait, in natural scenes,
I posted for you.
Yeah. Yeah, well, that's a question that we haven't looked at. I would think there would be, because there is quite a bit of evidence, for example, that in humans even there is a specialization for the horopter, the region where your stereo vision is better, is finest. This horopter has a shape that is slightly tilted, so that, for example, you are more sensitive for depths that are closer to you in the lower part of the visual field, as opposed to the upper part, which is, for example, related to the fact that probably when you walk, I mean, I was thinking of the horizon for this reason. When you walk, most of the time you need to look at things that are closer to you from the lower part of the visual field. So there are specializations of that kind. My expectation would be that they would be relatively small to measure using paradigms of the kind that I showed you here. Because already, for example, the effects that that I've shown you for inversion are difficult to measure. They tend to be quite small. And so I'm not sure whether they could be resolved experimentally, but I wouldn't be surprised if there were such, there were effects related to that, yes.
I don't think we have any more questions in the chat. I will ask everybody to just join the Zoom room and just share on the chat if you want to ask questions or continue this discussion with our guest today. It would be lovely if you can turn out your camera because we feel a little lonely now. That was the one. All right. Yeah, my connection is not good.
Okay.
Yeah, it's not the more talking crowd, I have to admit.
But that's, you know, I understand. Also because I don't know how many of you work in psychophysics, so.
I mean, not us, that's for sure, but that's definitely a topic that is interesting. I don't have the number of people watching right now. Hello, Tom.
Hello. that was great, Peter. That was really like, you know, we don't do so much psychophysics in the lab, but this I learned a lot. So this was really nice.
Thank you.
Interesting.
Yes. I had a follow-up question that Maxime didn't ask. So
Right.
how far are we away from linking any of these concepts to the actual firing of not large brain areas, but you know, networks of neurons or single neurons, that sort of level?
Yeah, so that's an interesting question, and so the slide I showed you with the work that Odilia Schwartz is doing, I think at the moment is the closest that we've got. There is also other work, of course. For example, if you take Jim DiCarlo's approach, but it's very different. The way Jim approaches it is, in my mind, is very large scale. There are these large population recordings, and then they attempt to use deep nets to model them. But again, already we don't have a good understanding of how the deep nets develop certain characteristics. So that makes it even harder than to understand, you know, what the neurons are doing, given that we don't have a clear understanding of the model. Whereas Odilia has a different approach. They are trying to use relatively simple local models. And then they sometimes do put a backend, which is a deep net, for example. But in that sense, they retain a little bit more connection with traditional neurophysiology in vision. And so if you look at her work, it's not to the level of interpreting an image, a natural scene. It more has to do with natural statistics in a more constrained definition. So it's not about, for example, knowing if an object is a glass or something else. It's more about figure ground boundaries and segregation. But for that, I have to say, in terms of the relationship with neurons, the work that she's doing is, I think it's very interesting. And that's pretty much as far as one could go, because then in terms of relating to human perception, it's, no, it's not, it's quite a long way.
Yeah. Thanks. Yeah.
Yeah, there's also the question of whether, I mean, you know, sometimes I really worry that we are not, but I mean, I'm talking for myself too, that we're looking at this from the wrong perspective. And I'm not sure that in attempting this link, we're looking at it the right way, in attempting to understand how perception relates to neurons. And so sometimes we get carried away because, for example, you know, I find that I can use the same model that a physiology uses, or, oh, I see Philip.
Philip, you understand that this is mirrored, right?
Yes. Well, but then, I mean, he's not, you're asking me to be Leonardo da Vinci there. So yes, sometimes I don't know if we are really looking at it from the right angle, and that's kind of worrisome, because it's easy sometimes to try and interpret behavioral data using neurophysiological data, or the other way around. But I'm not entirely sure, and that's why, for example, when I refer to top-down, but in any case, if there are questions, I'm going to answer the question. And Philip? Oh, so I have to go on to the, how do I get to that? So it's, so they are here. Okay, so I see a question. Could you elaborate on the filters used inside the probe? But is that a question relating to the stimulus or to the perceptual filters? Let me see.
I'm not sure this person is there anymore. But Ashley in the chat was wondering about the perception from B1.
Okay, so quick question.
Ashley?
Yeah.
You're mute. You're doing double mic. That won't help.
Well, so I see one question here from Asli about how can V1 be perceived so early? Okay, and then there was another question about the filters. That question, I don't, could you elaborate on this use of the probe? I'm not sure that I understand if it's about knowing how the stimulus was designed or the filters that are used by the model or the human observer. So if the person can clarify that, then I can answer. In relation to how can signals from early visual cortex be fed so early? Well, you know, that's not really known whether we can access or not signals that are that early. So it's possible, but we don't know. And there is a lot of, especially there was a time during which this entered the issue of consciousness, whether you can be aware of activity that is occurring very early in your visual cortex or not. And it has become less popular today, but in the 90s, it was a very popular question. So it's not impossible. And also keep in mind that when I talk from my own measurements, the ability that I have to pinpoint early visual cortex, I cannot say whether it's V1 or even V4. It's for the best I have in that respect is EEG. So it's those occipital measurements can refer to early visual cortex as defined as encompassing a lot of visual areas. So let me see. Okay, could you please go on?
Also, people who are not on the chat, I will read the question.
No,
Could
no,
you please evolutionary significance to align the perceptual filter with perceptual object? In my understanding, if you present a static picture, the system should adapt to it and respond more to significant changes from it. Or in your scenario, something deviated from object permutation. Not sure whether my understanding is applicable to high-level perceptual system.
Yes. So actually, I never thought about it that way. But one thing that I should comment on in relation to this is that you're right that if you present a static picture for a long time, that's what you would expect, perhaps. Is in natural vision. In natural vision, you wouldn't have that situation. Obviously, in natural vision, the image may appear when you make an eye movement, but they wouldn't be static for very long. You would have eye movements, you would have motion in the scene, and so on. So the issue of adaptation in this respect is a tricky one, and my data would have a hard time speaking to it, because so far most of the experiments I've done are with static images, which is already very unnatural for vision. Okay. But so, yeah, so I think there is something to what you're saying, but it wouldn't necessarily apply during natural vision because you don't look at static pictures.
Next.
Yeah.
Well, so maybe this is a bit off topic, but I was just curious, is there a statistical structure to the distribution of edges in a natural scene? So could like the visual area make a prediction of what an edge should be based on some edge that it saw, you know, previously or somewhere else?
Yeah, there is, although it's very dependent on the material you're looking at, obviously. So, you know, if you're looking at truly natural scenes, for example, forests or foliage and so on, the edge distribution is very different than artificial environments, meaning environments, you know, like offices and so on. And this has been looked at. So, for example, you can develop metric of edge co-occurrence or edge density. It's well known, for example, that edges tend to present a sort of Gestalt principle whereby they smoothly change orientation as you move away, just because they are along contours, for example. So there is structure like that, and it is possible that it is maintained from, say, one fixation to the other and so on. I don't know of any evidence to demonstrate it, but it is certainly possible that this is happening. I just don't, experimentally speaking, I don't know that there is any evidence to demonstrate it.
Thanks.
Yeah. By the way, one thing that I should mention is that the data set that I used for the experiments that I showed on the perceptually driven and image driven map, it's a very special data set. It's this data set called BST 500 from Berkeley, where they handpicked 500 images that present certain peculiarities that are interesting to computer vision. So they're not necessarily representative of the images you would normally see if you walk around. So that's also something to keep in mind, which is not a small problem. Some psychophysical results have been claimed to be due to artifacts, due to the choice of images and the kind of edge distribution that you get in images that are picked for whatever purpose, if it's computer vision in one case or so on. So that is a concern, yeah. Also methodologically, I mean.
So,
sorry.
yeah, go.
So it's more of a question about the random orientation stimulus using some sort of white noise. I couldn't fully see it in my head. So did you have a series of different wavelets in different orientations in each scene? You just sum them up, and then maybe your visual system with reverse correlation, you pull out an orientation, or was it a single orientation, but you just flipped them around?
No, they were all superimposed.
That's it. Okay. That's interesting.
You can do an experiment where you present individual gratings in succession, for example, in temporal succession, and it has been done. So in the early days of applying these techniques, people have tried that too. But in these experiments that I've done, no, they were all superimposed and presented quickly. Obviously, in the 2D pixel case, it was again just all the different pixels took a different value. And
so if you were to just see a single frame, it would just look like checkered white noise.
Pretty much, yeah. So it would look like a mixture. You wouldn't have one orientation, no.
Yeah,
if you just took it, and it was in those experiments, it was a fact. Yeah, it was one image. I've also done experiments with movies. So I haven't talked about those here. So in that case, it was different. Those were moving wavelets, and it was a different kind of experiment. But for these, it was a static one. By the way, this also brings up another methodological issues, which is that the oriented wavelets, that kind of noise, differs in an important way from the pixel noise, in that in the pixel noise, each noise element is truly independent. So each pixel you can set at a given intensity independently of the other ones. Whereas in the case of the wavelets, or the oriented wavelets, they're not orthogonal. So you can imagine that if two wavelets that are similarly oriented actually contain energy that leaks over from one to the other, so to speak. So this noise is not orthogonal, which is methodologically something that one has to handle essentially through computational modeling, because it does complicate a lot of aspects. Because in theory, the reverse correlation technique is designed for an input that is white. You shouldn't have correlations across the noise. So yeah.
Thanks.
Sorry for the mess. I don't know. Does anyone else want to ask a question?
Yeah, I have a question I'd like to ask.
Go ahead.
Hi, Peter. Nice talk.
Yeah.
And very good to see
hey,
you.
Simon, my goodness.
Yeah. So my question is about
So good to
what you were saying about trying to build a link to physiology. And one of the big problems I see there is that neurons have dynamics, and their responses change when the stimulus changes over time. And under natural viewing conditions, the retina is always moving.
Yes.
And so the neurons' temporal dynamics get modeled up with the spatial dynamics. And you're kind of looking at some sort of ensemble average of a population of filters, which will be flickering back and forwards across whatever this feature is, as far as I can understand it. And we don't have that bridge to the dynamics. And I don't even know, maybe somebody out there, Tom, somebody knows, in fact, what the effects of eye movements will be on, and just when I mean eye movements, I actually mean the tremor, which is always there in human vision. So the the drifts, what the effects of those drifts will be on the responses of neurons. And it would have to be responses of neurons which are actually in the fovea, because there's a tacit assumption here that everything you're doing is to do with foveate vision. And yet fovea is where we don't know very much actually about what V1 neurons are doing in humans, so my understanding anyway, because the receptive fields are so wretchedly small.
Yeah, well, but Tom, if you have something to say about this, I'd be interested in hearing your opinion. So one thing that I should mention is that the experiments I did, they did span the periphery as well, obviously. So the probes were placed in the periphery. And I did look at the, so now I'm not referring to the experiment where I did upside down inversion, but to the other ones where I was talking about the perceptually driven versus physical image and so on. In those experiments, I did analyze separately the effect away from the fovea onto the periphery, and actually surprisingly it was just constant and consistent across the visual field. I actually found that quite surprising. Let me see if I have an image to show you. So in this paper here, in this figure, you can see this effect. So I don't know if you see it, but here the top-down effect is, so what is plotted by, say, the green and the red traces here is, in this case, is the probability that a probe would appear, say, at the fovea. So they were more likely in the natural scenes to appear there. But also here is the sensitivity. So you can see that there is a big difference in sensitivity between rich and poor on the perception map near the fovea. But this difference persisted as you went into the periphery. And if you took the log ratio, it was pretty much constant.
Yeah.
So one thing to notice is that this effect is not foveal, so it does apply in the periphery too, and it seems to be of the same size. With relation to the issue of eye movements, so obviously observers were not allowed to move their eyes. There was always a fixation point here. So there were no eye movements, but as you say, there are microsaccades going on all the time. And the scale of those microsaccades, so here we're talking about stimuli that appeared sometimes, so I did different durations. I tested anything from 20 milliseconds nominally. It depends, I mean, what that really means in terms of visual stimulation is a different story because I didn't have post masks, but from 20 to 300 milliseconds, but no more than that. And the effect was always present, even at short durations. And then the third argument that I have against eye movements is the cueing argument. So if eye movements played a role in explaining this behavioral effect, then I would have expected a large influence of whether I was pre-cueing or post-cueing, because in the pre-cue case, observers would be tempted to, obviously, to move their eyes towards the cued location, whereas there was no effect of spatial cueing. So that is in relation to just a general issue of the role of eye movements and fovea versus periphery. Then there is the more important question that you ask is how, I mean, whether it makes sense to attempt to link between measurements of this kind that are taken for a static stimulus and the whole of perception and neurons that, you know, obviously have dynamics and, you know, I mean, as I said, as I was telling Tom, I think earlier, I think it's almost, I mean, it certainly is a question that one has to ask whether we are looking at it from the right perspective, whether it even makes sense to try and do such a thing. Because sometimes I really wonder whether it makes sense to to attempt this kind of link. And I'm not entirely convinced that it makes a lot of sense. I don't know what you think, but this is also what I was hinting at when I was talking about top-down. What does it mean to talk about top-down for a psychophysicist? I mean, for a physiologist, you could say, okay, I'm measuring from a neuron in V1. For the first 100 milliseconds, they don't respond to semantics. And then, you know, after 100 milliseconds, somehow they do. And so maybe it's some other area that's feeding in. But behaviorally, I'm not sure that I just don't see the argument in behavior measuring a top-down effect. I mean, for me, from the psychophysicist point of view, the notion of top-down is only meaningful if you can demonstrate that you have access to a representation without top-down and with top-down, if you see what I mean. So if you can demonstrate behaviorally using a purely behavioral measurements that say in the first 100 milliseconds, your behavior is driven by certain properties that are different than the following, and you are sure that you can do this because there are huge methodological problems with doing this with masks, for example, then I would buy that you're onto something that has to do with bottom up versus top down. Otherwise, to me, the distinction from a psychophysical perspective seems meaningless.
Well, I mean, the classic way of dealing with this was to use things like very brief presentations where you kind of minimize the effect of context. And when you do that, or use very uniform stimuli like sinusoidal gratings, then you find quite a good match between the properties of neurons and the properties of perception. And yes, that all fits together. The problem came because people discovered that these cortical neurons change their receptive fields depending on their context. And then you end up wondering why. I mean, because we can't explain it, I'm not sure I buy into your proposition that this means there's no bridge between physiology and behavior, because I might as well give up. I mean, well, it's too late for me. I've wasted my life.
Well, I'm not saying that there is no bridge. I'm saying that I think we may be looking at it from the wrong angle. So,
yeah, well, no, I agree with you there. I think we have to look at it from the right angle, and it's not clear to me what that angle will be, and that's why I raised this question of space and time.
And I think so. If I can follow up on your comments about presenting short stimuli, let me give you an example of how that actually may be the wrong angle. So if you present a very short stimulus, you don't know so that stimulus appears, but the observer keeps on processing the stimulus after the stimulus has disappeared, and you don't know how long it actually takes for that process to complete. So what you could say is, in the old days, what they used to do is they say, okay, I'm going to present a mask. The mask a high contrast mask will obliterate the stimulus, will interrupt visual processing. Well, it turns out that if you read the literature on masking, and I've asked people who work in masking as well, nobody believes it, because the problem with presenting a mask, particularly a very short duration, is that it interferes with the stimulus itself and it becomes one stimulus of its own.
Yeah.
And so to me, actually, it was disappointing to find that when I started thinking about ways of psychophysically measuring how long it takes for a process to complete, there's no convincing way of doing it psychophysically. That's why I use the EEG, because at least with EEG, if I pick up some relevant signals within a short time window, well, you know, I have a real-time readout of what's going on. How that relates to behavior is a whole different story, but so it's not obvious to me that you can just do an experiment with a short stimulus and claim that you're looking at, you know, short perceptual processes. So then what do you do? I don't know. Yeah.
So could it be useful to use simpler animal models to try to get something like, I mean, they have to still subtract, you know, distinguish the foreground from the background based on object shapes and things like that. So they do this higher level stuff, and there we're also not quite sure how they do it, but presumably finding the neurons that do it is a bit easier, I wonder.
Yeah, and of course, I mean, that's the fascination with using, I mean, well, that's part, I mean, there are many aspects to studying, well, simpler, let's call, you know, creatures that we can perhaps understand. And I agree with you, yes. And I'm sure you guys have a lot more to say about this than I do. Although, I mean,
if only, right? That's the problem. We don't really know how to do this because it's well, the bridge is still missing, I guess, right? But if we had a bunch of neurons, say in the fish brain, that told us this is foreground, this is background, that would be quite neat. Just not sure how to get there. Yeah.
but you would still need to show the relationship to the behavior of the fish.
Right. Yeah.
And that's a tricky one to demonstrate. So
so this is something that I wondered that, that I think relates to the question with sort of transferring these techniques to different animals, and that whether something is to the right of something that is to the left, and questions such as, I don't know, if something is oriented away from the vertical, these are very unambiguous, right? So we're benefiting in humans with sort of unambiguous language. There's only one way in which one can interpret really what the person is in a way indicating, right?
Yeah.
But it is not the same way with animals. So do you think that we need some sort of categories, that we need sort of more necessary categories that we could explore behaviorally?
But you mean in animals or in humans?
Well, both really. I mean, the entire point is that sort of contrast is what defines that, whether something is, to the left of something that is to the right, and that is a necessary category of perception or thinking, right? Like these words are unambiguous, as opposed to any other behavior that we can sort of show. I just wondered what.
Yeah. By the way, let me say that this is not the case. So in psychophysics, as soon as you start having stimuli of any complexity, you cannot be sure that observers that those terms are well defined, because especially if you use feedback, observers will use any cue that will get them the right answer. Whether that cue is the one that you originally posed to them as being the task is, you don't know. So, it's not necessarily the case, just to give you an example, that an observer, if you ask them to do an orientation discrimination, that they will actually use their orientation perception to do it. If there are other cues in the stimulus that will support performance, they will use them.
Right, but that's the thing, like because you also made this distinction between object segmentation and semantics, like why, like basically why we need certain objects, right? And this is like the way it relates to my previous question is basically sort of this, right? So if I'm a fish or if I'm a rat, right, and I see a blob, right, like do I at that point, is there anything in my brain going, where is it? Is it to the left or to the right, or is it just going food, right? Like sort of what are the necessary categories that we need to define in order to even explain the data? Right?
Yeah, no, I agree with you. But for example, if you were to do it behaviorally, you have to ask yourself whether you're asking the animal to do, or whether the animal is doing what you think the animal is doing, which, by the way, in my experience with fish, was almost never the case. I mean, I remember doing some experiments with zebrafish where I thought I would be able to predict the preference of the animal on the next series of stimuli I had planned. And then the animal did something completely different, which obviously meant that my way of thinking about what the animal was doing was completely wrong. And so it's a problematic question that you ask, because I think actually maybe going back to what we were saying before, that sadly, it may be the case that, as Simon said, at least as far as I'm concerned, I've just been wasting my time, because if we are looking at it,
I know I was wasting my
time. No, but I'm worried about, of course, we're all worried about that. But the point is, if we start, I mean, psychophysicists get so focused, they think they know this is the right approach, and they keep on doing it that way. And then, you ask yourself whether the physiologist is doing the right way, and so on. And these questions are relevant, whether even the whole scaffold has any viability here. And I'm not entirely convinced, honestly.
Well, to put a positive spin on what you would say, I mean, on what you're saying, I would say that's what's really interesting about your work is that you produce non-physiological evidence that these cortical mechanisms retune in response to context.
Yeah.
And that's very, very important because the physiologists have measured all these things, or measured phenomena that fall in that general class, but whether they actually help you see things or not is a different matter. And your experiments suggest that they do. I mean, I think the one thing you haven't done is take a sort of functional approach and say, well, how in fact would they help you see? What could you do better with a mechanism like this than something that's just a dumb filter that doesn't retune itself?
Yeah. No, I understand exactly what you're getting at.
But if you look at, you know, I'm showing my age here, but if you look at color vision, right? Now, you were saying about confounding variables. Well, color vision's only got 3 variables in a human, maybe 4 if you allow a bit of rod in. And we can understand everything about color mixture at the level of blank scenes and uniform illuminance. And we can explain that in terms of quantum catches by photopigments. The problems, the things we don't understand about color vision are all about context, about a color seen relative to various other colors, or colors associated with shapes and so on. And the big problem with the brain is that the brains have evolved to make meaningful connections, to take advantage of correlations to be better informed and more certain about what's going on. And they're incredibly good at it. So you have all of these marginal effects which tweak the system up to work a little bit better. That's one interpretation. The other is that it goes into some giant mathematical master transform, which some genius figures out, gives you everything that you ever want to know.
Yeah, so I mean, you know, quickly, I would say in relation to the 2 questions. So the second question is much more, you know, I think it's a very difficult one for me to answer, which is why would you need these mechanisms? What are they useful for, and so on? And that, as you say, I mean, I have some ideas, but I certainly don't have a conclusive demonstration of why would help, for example, for the circuitry to be reshaped a certain way and so on. But in relation to the first question, what worries me is, so thank you. You know, it's great to imagine that I'm showing that these signals percolate all the way to behavior. But let me play devil's advocate. So I'm approaching this from a perspective that is informed by physiology. So I'm already starting out with maybe a Gabor wavelets, or a lot of my thinking is about localized receptive fields. And so my concern is that the reason why I'm reporting and measuring this stuff is simply that I'm already starting out, well, on the right foot in order to demonstrate it, but on the wrong foot in order to actually take a perspective that is unbiased, if you see what I mean.
Yeah.
So it's almost as though my experiments are already designed with that particular objective in mind, and therefore are informed by the way physiologists have done it and so on. And that is a concern.
Yeah. Yes.
And I don't see much of a way around that, because it is so difficult to completely remove yourself from that knowledge and design something completely different. But yeah, so that is something that I'm concerned about in terms of approaching this behaviorally.
But it is very interesting that your data sort of show that something that we thought was very intuitive about optimality does not quite pan out, right? I mean, like, it's understandable that sort of fewer people would actually raise these questions because you've seen sort of the like in action that some sort of premises just do not hold, really.
Yeah, also optimality is a really difficult. I mean, the question that Simon asked is a question that you can answer in limited context. I mean, if you have a simple, in the context of signal detection, for example, signal detection
Right.
theory, you can you can resolve those issues quite well. And I mean, you can even write down equations and solve them, and that's fine. And you can find interesting stuff that you can then try and confirm experimentally or not, and so on. But as soon as you start moving into something like natural scenes and in scene interpretation, and it's so difficult to even quantify the targets that you need to optimize. Your target metric is very, sometimes it's not well defined, and so it's very difficult to just come out with a good way of you know.
Well, it's more the question of whether we can move the other way around, right? Of whether we can see something in perception or in the brain that seems to be optimal for this, and then say, oh, this is therefore a metric in a way, right? I mean, that's sort of the way half of thinking goes, I think.
Yeah, I mean, but I don't know if that would be satisfactory. I mean, that really depends, because then if you're just using your own data to define your metric, and but I mean, by the way, psychophysics, sometimes you find, I in some work that I published recently, I measure very simple properties like detection of just isolated targets and very contrast. And actually, Simon, I was telling Simon about this data some time ago. I ended up publishing that data, Simon, the one where I showed that at low contrast, it turns out that your perceptual system becomes more bandpass rather than low pass in human vision, which is completely against all theories of optimality, all theories of, you know, it is not what you would expect based on optimality theory. And I don't know why. I mean,
sorry, did you say in low contrast it shifted to bandwidth?
Yeah, so for example, if you measure, say, a filter like kind of like the ones that I showed you, they're not exactly like that, but kind of like the 2D filter for a wavelet, or, you know, so it has a shape that can be either band pass, like a Mexican hash shape, or it can be low pass. It can just be a Gaussian. So when you measure that as a function of contrast, what you find for detecting a line, for example, is that at high contrast, it looks pretty low pass. And then as you lower contrast, it becomes more and more bandpass. And this is not at all what you would expect, you know, based on, well, you know, I mean, Simon knows a lot about this stuff. So if you have a theory where you're trying to do noise averaging, then a low contrast, you should be more low pass, in fact. And
well, it all depends. Well, it depends what noise you're trying to actually, your signal is being resolved against. So if it's input noise, then you want to lower the back, you want to go to low pass. But if it was intrinsic noise at some higher level, you might actually want to sharpen the filter. Then you would get a bigger signal, and that would show up better against the noise. That would suggest, why isn't the filter sharp all the time? That suggests that there's some penalty to having a sharp filter, like it's very sensitive to small spatial shifts, for example.
Yeah, so I looked into this because the issue of intrinsic versus extrinsic noise is obviously critical. And in humans, by the way, you cannot do an experiment without intrinsic noise. I mean, there's no way. And it's much bigger than in neurons. So I measure extrinsic noise also as a function of contrast. So if you measure it, if you just measure using a standard technique in psychophysics, what you find is that intrinsic noise goes up at low contrast. Yeah. You're noisier internally. But if you, oh yeah, Tom, you, bye. No, I just got a message. So and that's fine. If you measure, you will find that it goes down, that it goes up. But then that doesn't mean that actually the intrinsic noise source goes up or down in the model, because you can model all of this, for example, with a constant intrinsic source. But I mean, it's a very difficult issue because these two things go hand in hand. And so to try and disentangle them, I mean, I'm talking about behavior here still. And so it's, you may be right or you may be wrong, Simon. I mean, the problem is that it's very difficult. From the data I have, for example, another thing that I observe, which is striking and it's large, is that at low contrast, the system becomes highly nonlinear. Whereas, so imagine the way I would describe this, imagine it becomes like a complex cell. So it basically does energy processing with with bandpass filters that are stacked as a bank, and then it just squares. So it does energy at low contrast. At high contrast, it behaves much more like a linear template. So then, even that, why does that happen? I mean, I'm on the basis of optimality theory, it's not clear. I mean, you know exactly where the target is in these experiments. It's spatially localized, perfectly indicated. There is no uncertainty, spatial uncertainty. And yet you see huge effects of contrast on these measurements that are, as far as I can tell, they're inconsistent with, or at least it's not clear how they relate to optimality. Yeah.
So like Tom, I'm going to have to go now. So
yeah, well,
thank you very much. It's very stimulating, Peter.
No, thank you, Sam.
Okay.
It was great chatting with you.
Yeah, yeah, it's great to see you. Yeah.
We'll have to, well, anyway, well, at some point we may organize a chat.
That would be very good.
Yeah,
okay.
So that I can catch up with you.
Yeah, yeah. Let's do that. Okay. Bye.
Okay. Bye-bye.
Bye.
I should probably go too. Thanks for organising the talk,
guys.
and thanks for a great talk.
Thank you, guys. It was great.
Thank you, Peter.
So I think we can all go, right? Or you have, if you have questions.
I mean, I would have questions for you. I think Maxime is the organizer. So first of all, I have to say sorry for the technical issue.
No, that's fine.
I don't know what happened. It just literally, I could not hear the Zoom at all. No, but well, actually, so first, I actually wanted to respond to Simon in that something he mentioned about color vision and how, but it might also be relevant to our discussion with the semantics bit, right? Because Daniel Osorio, right, and his student Lucas Wilkins, so they've introduced for chromaticity, and of course this is what the lab is all about, right? So color vision. They've introduced a metric of vividness. Are you familiar with the work at all?
No, vividness, no.
Well, the idea